Welcome back to the deep dive. AI, it's just advancing at this incredible pace, right? Generating images, writing code. But one area that's always been really tough is scientific research. So what if there was an open source model, not just okay at science, but genuinely exceptional, like something that could really accelerate discovery? Today, we're doing a deep dive into a paper called INTERN-S1, a scientific multimodal foundation model. And this isn't, just another LLM. It's pitched as a specialized generalist, really aiming to push towards AGI, but specifically through scientific breakthroughs. Our mission today, unpack how it works, the architecture, the training, and what it means for open science.
Exactly. And for a long time, open source models, they really lagged behind the closed source ones in these high-value scientific areas. INTERN-S1 just tackles that head on. It's bridging the gap, and honestly, in quite a few specific professional tasks, it's actually beating the closed source state-of-the-art. It feels like a real step change.
Okay, let's try and give you the quick version, the shortcut. Especially for, fellow researchers, ML engineers listening in. Here's the TLDR on INTERN-S1. It's a new multimodal mixture of experts MoE foundation model. Came out of Shanghai AI Laboratory, and it's really designed to, shake up scientific AI.
Right. The key thing to grasp is that INTERN-S1 isn't just trying to catch up. It's actively challenging the dominance of proprietary models in science. We're seeing it significantly outperform the existing open source options. But also surpassing closed source leaders in really specific things like molecular synthesis planning or predicting reaction conditions, even crystal stability predictions, stuff that's core to chemistry and materials science.
And how's it doing that? Well, scale is part of it. It's huge. 28 billion activated parameters, 241 billion total. It's been continually pre-trained on, get this, 5 trillion tokens. And the kicker is, over half of that, 2.5 trillion, is scientific data. That's a massive commitment.
Yeah. And it's not just the scale, it's the smarts, too. That novel dynamic tokenizer they developed. It's a big deal for handling things like smile strings in chemistry. Gets something like a 70% better compression ratio. And then there's the mixture of rewards framework. More for the reinforcement learning part. Super efficient way to train across over 1,000 different tasks at once.
Best part for us. The weights are open source. They're up on Hugging Face, so you can actually get your hands on it, explore it, build with it. It's not just a paper. It's a tool being shared.
You mentioned something earlier I want to circle back to, this idea of scientific research as an ultimate goal for AGI. Why is science so much harder for AI? What makes it different from, say, understanding images or writing code, where we've seen such huge progress? That's a really good question. It gets right to the core of why INTERN-S1 exists, I think. Scientific research, it's not just about, processing information you're given. It demands that models understand the deep underlying laws, often hidden laws, governing really diverse, sometimes low-resource scientific data. Think about complex molecules, right? Or subtle patterns in, gravitational wave signals. It's finding the needle in the haystack. And then it needs rigorous long-term reasoning. You need to form a hypothesis, figure out how to test it, maybe design an experiment, then evaluate the results. It's a much deeper kind of intelligence than just pattern matching.
I see. So even though open source is caught up amazingly in areas like natural images or even math problem solving, sometimes beating the big guys, scientific discovery itself has remained this really tough nut to crack.
Exactly. And the paper shows this quite clearly, actually. You see these charts where general LLM performance shoots up on popular benchmarks, but the line for scientific tasks stays kind of flat or lags way behind. There's this substantial gap, as they call it. And INTERN-S1 is designed specifically to jump into that gap, push open source towards AGI, but through the lens of science. It aims to be, a foundational tool, one that can really accelerate discovery because it gets not just general stuff, but the specific, specialized, often weird data formats and concepts in science, like giving it, specialized glasses for chemistry, physics, biology.
That makes sense. A specialized generalist, as you said. It's okay, powerful vision. How does the architecture actually enable that? Let's get under the hood. It's built on a multimodal mixture of experts LLM. Can you quickly unpack why MoE is a good fit here for tackling such diverse scientific challenges?
Sure. So MoE, mixture of experts, the basic idea is you have this big model, but for any given input, you only activate a small subset of expert networks within it. Think of it like having, I don't know, a huge team of specialists, but you only call up the 2 or 3 most relevant ones for the specific problem at hand. This makes it incredibly efficient computationally, especially when you're dealing with wildly different types of data and tasks, which is exactly the case in science. INTERN-S1 uses the Quin3235B architecture, or the smaller 8B for the mini version, but the key is how it routes the different kinds of scientific data. They sort of categorize modalities into 3 types, and each gets its own tailored projection strategy to talk to the LLM. So first, you've got your visualizable representations, things like weather maps, microscopy images, figures from papers. For that, it uses the Intern-VT series encoders. These are known for being really good at high-resolution, fine-grained visual stuff. They use this technique called pixel unshuffle. It's a clever way to reduce the number of visual tokens without losing critical detail. Then an MLP projector aligns it with the language model.
Okay, and then you mentioned that dynamic tokenizer. That sounded really interesting, especially for structured data. You talked about smiles strings for molecules. Walk us through why that's such a big deal.
Right. This is, I think, one of the really clever innovations here. So chemists use smiles, this text-based notation like smile CU1 CCCCC1 smiles, to represent molecules. It's super common. But standard tokenizers, the ones trained on general web text, they're terrible at this. Smile syntax is rare in normal text, so they don't compress it well. And worse, a character like C for carbon ends up sharing the same digital representation, the same embedding, whether it's in a molecule or a DNA sequence or just the letter C in a sentence. That introduces bias, right? It muddles the meaning. So the dynamic tokenizer, what it does is it first detects these patterns. It looks for tags like smiles, or it uses chemical toolkits like RDKit to recognize chemical notation heuristically. Then it segments the input. And here's the crucial part. It applies different splitting rules to the scientific part versus the general text part. And it makes sure their embedding spaces are kept separate or orthogonal. So the C in a carbon ring now means something different to the model than the C in cat. Much more precise.
Wow, okay. And that leads to a 70% higher compression ratio, you said. Compared to things like GPT or Quin tokenizers on this kind of data, what does it actually mean for a researcher using this? What bottlenecks does that break down?
Yeah, that 70% isn't just, a nice number. It has real consequences. Think about processing huge chemical libraries or genomic databases. Fewer tokens means less computation. It means faster processing, less memory usage. It means you can potentially analyze much larger data sets than before or run complex simulations that were just too expensive. It could genuinely speed up things like drug discovery or materials design just by making the data handling more efficient and accurate. It removes a practical barrier. And the third category they handle is time series signals, seismic waves, EEG, gravitational waves, data that's long, continuous, kind of messy. They have a dedicated encoder for that too, which captures the temporal dependencies, does some adaptive downsampling, basically makes sense of that stream-like data for the LLM. So each data type gets its own specialist.
Okay, brilliant architecture, clever tokenizer, but you need the right fuel for that engine. The data and training must have been immense. What did that involve for INTERN-S1?
Oh, immense is the right word. It was a massive effort. The continued pre-training alone had 4 stages. And the data set, 5 trillion tokens total, but over 2.5 trillion specifically from scientific domains. That level of commitment to scientific data is pretty unprecedented for an open model, and getting that data clean and usable required some serious engineering. Take their scientific data pipeline. For PDFs, which are, the bedrock of scientific literature, they built this hybrid OCR and VLM system. Parsing scientific PDFs is hard equations, symbols, complex layouts. So they used a cheaper parser, minor U, for most pages. But if it flagged a page as potentially tricky, maybe with complex math, then it got sent to a more powerful but slower and more expensive VLM, like INTERN-VL. It's a smart cost-benefit trade-off. They also did things like global deduplication across pages and filtering out garbled text, really focusing on quality.
And what about web data? Just scraping science websites isn't enough, right?
No, exactly. Their domain-centric web data parsing was neat. They grouped pages by domain, like all the pages from nature.com. Then they used an LLM agent to sample pages from each domain and decide, keep it, rewrite it, or toss it. It's much more fine-grained than typical classifiers, catching things like weird navigation bars or badly extracted code snippets that could pollute the data.
And filtering. How do they ensure they actually got the right scientific content?
Through their scientific data recall and filtering stage, they set up this detailed taxonomy across 6 domains: math, physics, chemistry, life science, earth science, material science. Then they used a powerful LLM to annotate examples and trained lightweight classifiers based on that. This massively boosted the proportion of relevant scientific data in their training mix from maybe 2% initially to over 50%. Really targeted curation.
And this extended to multimodal data too, not just text.
Absolutely. The multimodal scientific data pipeline was just as rigorous. They didn't just dump images next to text. They focused on preserving the structure figures, equations, tables, making sure visual elements were correctly aligned with the text descriptions, and even creating instruction-following data based on scientific diagrams or exam questions. They even used VLMs to double-check if equations were rendered correctly. It's like building a really high-quality interactive textbook for the AI.
Okay, so the data is top-notch. What about the training process itself? Any clever tricks there?
Yeah, a couple interesting things. One was the batch size warm-up. They noticed empirically that starting training with smaller batches helped performance early on, but larger batches were more efficient later. So they just did that. Started with a smaller batch size, maybe 4 million tokens, trained for a while, then switched to a larger one, like 10 million tokens. The paper shows a clear benefit to doing this.
And they seem to have incredible control over the training process.
Right, the Hyperparameter Control. Using their framework, XDuner, they got really precise. Their scaling law models predicted a final loss around 1.16, and the actual model landed between 1.17 and 1.18. That's like 0.02 precision on the loss. It shows a really mature, predictable training setup.
Which is crucial for these huge, expensive runs.
Exactly. And one more thing. Joint multimodal training. They made a point of updating all the parameters, vision encoders, language model, everything during the multimodal training phases. They didn't freeze parts of the model, which is sometimes done. They argue this allows for better, deeper integration of the visual and textual information. Seems plausible it contributes to the strong multimodal results.
Okay, so pre-training is done, then comes post-training, reinforcement learning. And you mentioned it learns from over 1,000 diverse tasks simultaneously. How on earth do you manage that? That sounds incredibly complex.
It is complex. And that's where the mixture of rewards, the more framework, is key. Think of it as an orchestra conductor for reward signals. MoE takes all these different signals from logical puzzles, academic benchmarks, following instructions, visual Q&A, just general chat quality, and integrates them. This cross-task optimization is what lets INTERN-S1 become a deep specialist in science without forgetting how to have a normal conversation or reason generally. They also use a smart hybrid offline data filtering strategy because, some tasks are harder, some converge faster. It helps balance everything out, avoid overfitting one task while underfitting another.
And where do these tasks and rewards come from?
A few places. They use Intern Bootcamp, which is this cool interactive environment they built. It generates basically unlimited synthetic reasoning tasks, algorithms, crypto, physics problems, great for RL training data. For multimodal stuff, they built specific high-quality data sets where they knew the ground truth answers. And they use a mix of verifiers, their own lightweight one called Compass Verifier, and just straightforward rule-based checks to assess correctness robustly. And then for general alignment, making sure it behaves well in open-ended chat, they lean on Polar 7B. That's a reward model trained specifically to judge the relative quality between different AI responses, which scales better. So, whole suite of tools.
You also mentioned RL for MoE models had specific challenges, something about instability.
Yes, that's a really important technical point. Older RL algorithms, like GRPO, they ran into trouble with MoE models. There were discrepancies between how the model selected experts during inference versus during training updates. This caused instability, expert mismatch, basically made RL hard for MoEs.
Okay, so how did INTERN-S1 solve that? They used a different algorithm.
They adopted Oreo, yeah. It's a newer algorithm that inherently avoids some of the issues like token level clipping that caused problems before. But when they tried to simplify Oreo further by removing a token level reward model, which would speed things up, they hit another problem. The model's entropy dropped too fast.
Meaning it stopped exploring, it just kind of locked onto suboptimal solutions.
Exactly. It lost its ability to explore different strategies, which is crucial for effective RL. So they needed a fix. They brought in ideas from policy drift control and something called the Kale-Kov strategy. Essentially, they added a constraint term to the loss function that penalizes the model if its internal state diversity entropy drops too low. And it worked. The paper shows this technique kept the entropy nicely stable throughout training, allowing the model to keep exploring while its correctness on tasks steadily improved. The upshot was a 10x reduction in RL training time compared to standard baselines. That's a huge efficiency win, making this kind of sophisticated alignment feasible. Think about how much faster you could iterate or refine the model with that kind of speed up.
Okay, so connecting all these pieces, the architecture, the tokenizer, the massive data, the sophisticated MoE and RL strategy. let's get to the bottom line. How does INTERN-S1 actually perform? Does it live up to the hype?
Well, based on the paper's results, yeah, it really does seem to deliver. It's a genuine step forward, especially for open source science AI. Let's break it down. First, general reasoning. On benchmarks like MMLU Pro, GPQA, AME 2025, INTERN-S1 comes out as the top open source multimodal model. It does particularly well on visual math reasoning. Got the highest score on Math Vista, 81.5. That's like almost 20 points higher than previous open MLLMs on Math Vision. Huge jump. Now, it still trails some of the top proprietary models, like maybe GPT-4, on purely text-based reasoning like GPQA or iFeeble, but it's very competitive on things like the AMA math competition problems, so strong general skills.
But the real test was the scientific benchmarks, right?
Right.
That's what it was built for. How did it do there?
This is where it truly pulls ahead of the open source pack and even challenges the closed ones. On text-only scientific benchmarks, things like Small Instruct for chemistry, ChemBench, MapBench for material science, INTERN-S1 takes the top spot overall on 3 out of the 4 main ones they report, often by really significant margins. Like that plus 25.7-point lead on MapBench over other open models, that's massive. For a material scientist, that difference isn't trivial. It could mean much more reliable predictions about material properties, potentially cutting down experimental time or even suggesting novel compounds. That's real impact potential.
And multimodal scientific tasks, like interpreting charts or diagrams.
Same story, really. On multimodal scientific benchmarks, SFE, physics benchmarks, micro-VQA, MS-Earth MCQ, XLRS bench across these diverse scientific domains, INTERN-S1 gets the best overall scores on 4 out of the 5 datasets tested. And it's a strong second on the 5th one, physics. So yeah, it's not just closing the gap. In many of these specialized scientific reasoning tasks, both text and multimodal, it's setting a new high bar for open source and frequently surpassing what even the proprietary models can do in those specific professional niches.
And quickly, the INTERN-S1 mini version, is it just a toy or genuinely useful?
Surprisingly capable. Even the mini version, the 8B parameter one, it achieves the top open source score on 11 out of the 17 benchmarks they tested across both general and scientific tasks. So it proves to be a really strong, lightweight scientific reasoner, very powerful for its size, which is great for accessibility, makes this kind of capability usable on less demanding hardware.
Wow. Okay, what a deep dive that was into INTERN-S1. It really does feel like a significant step, doesn't it? Especially pushing towards AGI within that really challenging scientific domain. It's like the open source world just got a major research upgrade.
Absolutely. You put together the huge scientific pre-training data set, the architectural innovations like that dynamic tokenizer, the very efficient and sophisticated reinforcement learning with more to know. It's more than just another big model. It really showcases the power you can get from building these specialized generalists. It's a new benchmark for what open source AI can achieve in demanding fields like science.
And crucially, it is open source. The weights are on Hugging Face. People can download it, experiment, build on it. That democratization aspect is huge.
Which leads to, I think, a really interesting question for you listening. How quickly now will open source models, fueled by these kinds of specialized, powerful systems like INTERN-S1, start to really reshape scientific discovery? Will we see advanced research tools become accessible to everyone, everywhere? Think about researchers who maybe didn't have access to the biggest proprietary models before. Could this accelerate breakthroughs across the board? What could it mean for your specific field or the challenges you're working on?
Something to definitely think about. What could you build with this? We'll leave you with that thought. See you next time for another deep dive.